okay? But starting with the Earth, okay, the Earth has a, that gray-looking thing is actually our core, okay, the Earth's core, like the movie, The Core. And it's like very heavy with regard to the type of material that's there, heavy elements. And then we have a mantle, okay. Actually, we have a solid mantle and a liquid mantle. And then on top of the mantle, we have the lithosphere. Okay, so there's the lithosphere. And on top of the lithosphere, we have the crust. Actually, the lithosphere is the top part of the mantle and the crust. Okay. So how do we know what is the interior of the Earth like? Well, it goes to seismology. So basically what seismology is, if you've heard of, like, you know, the earthquakes, they get out there and they kind of look at the Earth shaking. Well, that is energy, and that energy from, like, for instance, an earthquake travels differently through these different layers. Okay, and so they can get a sense for where those layers are and what, and the kind of the nature of the layers. So all of these objects here in a minute we're going to see have a core, mantle, and crust. Okay, the lithosphere, like you saw me kind of stumble a little bit, the lithosphere, as it turns out, is the top part of the mantle and the crust. That is the lithosphere. Final answer. Okay. So here we go. Here are the other objects. Now they're kind of scrambled now. They're scrambled in order of decreasing size. So the Earth, in putting the moon in there, but the Earth relative to the other terrestrial planets is the largest, and that actually has consequences. Then notice Venus actually is relatively close size-wise to the Earth. Mars is significantly smaller. Mercury is even smaller, and the moon is smaller than Mercury. Okay, so how do we know then these other planets? Okay, I always think of the movie Tremors when I think of seismology, where I think in one of the episodes, you know, there's been, like, I don't know, 3 Tremors movies made, but basically, actually there was a seismologist out there, and all of a sudden it starts on the ground, it starts going. So one of those things where we're sending a shockwave through the ground. But, you know, we can't visit, or we haven't visited. I don't think we visited specifically for this. We visited some of the planets, specifically Mars and Venus a little bit. But the way we know the composition of these guys is actually to understand the composition of our own and to put other things together. For instance, we're going to look at the Earth's magnetic. Earth has a magnetic field. It's really kind of good for us. And the fact that the Earth has a magnetic field is an indication of what's happening in the Earth's interior. All right. So we definitely have this layer thing going on. Like I said, that gray core, or the heavier elements, literally, like the precious metals and stuff like that, basically have fallen to the Earth's core. Maybe that's why they tried to, like, tunnel to the core to get those precious metals. And I don't know. It's a movie, The Core, actually. Yeah. So one of the things we're going to talk about is, are these objects still geologically active? Okay, do they still have volcanoes and that sort of thing? Well, in order to be geologically active, they have to have some, I call it ooey-gooeyness to them. Early on, actually, all of the planets were ooey-gooey. That's to say they had a lot of heat from just being formed. And this says, why did they have heat? Well, 2 reasons. One is basically just like we talked about our collapsing solar nebula, turning potential gravitational potential energy into kinetic energy. So also that happened for the planets. The other thing about the planets is that just this radioactive decay that we kind of talked about. How do you radiometrically date meteorites to know that the solar system is about 4.6 billion years? Argon decays into, or potassium decays into argon, and it releases energy. So that's radioactive decay that can also heat the planets. Okay, so think ooey-gooey. I've never really written ooey-gooey on a slide, but I say it a lot. Okay, so the planets were ooey-gooey, and so all the planets could go ahead, and it's like planetary differentiation. This term up here is really like salad dressing. I think your textbook, Italian oil salad dressing. Okay, so basically you shake it up, okay, and let's see, how does that go? I think your water sinks and your oil rises. Okay, it's a density thing. Okay, and that's the same thing that happened with the planets, except it was heavy things were sinking to the center and lighter things were rising. Okay, so that's kind of how they all kind of have that differentiation with those colors, those different elements, heavier elements, and then the lighter elements. Planetary differentiation. Salad dressing. All right. So remember that 4.6 or 4.5 billion years is an important date. I think it came up on your unit exam. But that's when our sun turned on, okay, some 4.5 or 4.6 billion years ago. And so ever since then, the material that made the planet was kind of already there, okay, so then it could begin cooling. Okay. So like I said, are these planets geologically active? Well, they need to have some sort of residual liquid in them to be geologically active, quite frankly. And we're going to see that in a minute. Okay. So here they are, the same ranking. These are actually from largest to smallest, and you can get a sense for the size of their cores. I think it's interesting. I don't have, I guess we do have a little explanation. But can you see where the moon doesn't have much heavy stuff? Okay, the moon's gray is really kind of small. Actually, that goes along with how the moon was formed. Remember, the moon was a piece of the Earth, okay? After the Earth started to differentiate, okay? So basically, it kind of got the lighter stuff from the Earth. But little Mercury, oh my gosh. It could be because the condensation temperature of the lighter stuff is lower than the condensation temperature of the metals. So I don't know. Heavier things. So we have largest to smallest, okay? So the term plate tectonics, you've probably run into it before, plate tectonics on Earth. Basically that is, and we're going to see a picture of it here in this chapter, is where you can actually look at the Earth's, I want to say lithosphere. Basically it's slabs of crust that float around on liquid mantle, okay? That's kind of plate tectonics. All right, here we go. Dead, okay? That's to say the moon and Mercury, if you were to look in their interior, they're not ooey-gooey at all. Okay, they don't have any liquid or plate tectonics, okay? And actually, does this make sense that little things cool off more quickly, okay, than large things? And that's exactly what's happening here. They just cooled off more quickly. Okay, the Earth, geologically active. Venus, also geologically active. Do you remember, though, Venus is a tough cat to study, though, because Venus actually has those thick clouds. We really can't peer in it at Venus very good. Okay, we get a sense for its topography using radar, okay, so Venus. But, and as far as I know, only the Soviets have landed a craft on Venus. And we're going to see an image in this chapter of the surface of Venus as sent back by the probe that landed on Venus. But Venus is geologically active. That leaves Mars, okay? And at the time I prepared these, you know, I haven't checked it recently, but it's a little bit up for grabs, whether Mars actually has some liquid mantle to it, or liquid, mantle to it, or not. But definitely we have the size. So the larger Earth and the larger Venus, they could retain their heat longer. So this reminds me of, remember we said a criteria for something to be a planet is that it needs to orbit the sun, and that object needs to be spherical. Okay, and that kind of reminds me of this. Actually, you could take a large object that was a cube, and if it was large enough, give it enough time, and let's go ahead and make it rock and granite. Okay, give it enough time, that granite thing is going to deform over time into a sphere. It just will. Okay, so solids can deform, but over time, then you kind of get this rounding thing. If you go ahead and take a force and apply a force abruptly, it's going to fracture, kind of like silly putty does. If you take silly putty and kind of mold it to how you want it to, or pull it out to how you want it to, slowly you can. But if you take silly putty and apply a quick force, it's going to fracture. So that's kind of the same way rocks do. I think it's kind of amazing. Rocks can deform over time. I'm trying to think if you've ever, like in a real deal, seen rocks deform. If you take like flat asphalt, don't you, in my own mind, I can almost picture, you know, applying some force, and I don't know how great that force would be, something with a great mass. Over time, it will go ahead and kind of create a little divot.
Why not erosion?
What's that?
Why not just general water erosion?
Well, that's true too. Yeah, it's another way to resurface. So the planets cool down. How did the planets cool down? And actually, we kind of have three modes in which heat can be transferred here, okay? Described here with the planet, and it's the same way with just regular heat anytime. Heat can move via convection. Basically, convection is a blob moving, okay? So literally, this would have to be in the ooey gooey parts of the inner planet, where you can have a blob of warm stuff moving from the core outwards, okay? Oops, yeah, core outwards. So it moves from the core outwards, and then it cools off when it gets closer to the Earth's surface. Okay, so this is convection. So this is very hot, okay? And so this is liquid here, and it moves up. A whole blob relocates up here, and then it cools down, and then it sinks back down. Okay, and then it heats back up, and then it comes back up. This is actually called a convection cell. Kind of get a sense for that. This says how long does it take for a blob to go up and come back down? Okay, 100 MY stands for million years. 100 million years to make one round trip convection. Okay, so heat actually is relocated from the core outwards. Well, once it gets then to the lithosphere, okay, that actually would be this yellow part and kind of the bottom, the crust part, and then part of the top part of the mantle. Then something else happens, and it's called conduction. So conduction is another way from heat to get from point A, thermal energy to get from point A to point B. This is actually what I call the kind of butt to butt to butt sort of thing. Conduction, a good example of conduction is if you are heating something on the stove and your handle, you're using a pot with a long handle, okay, and your handle gets hot eventually. That's because of conduction. Because basically, your pan got hot first, and then molecule to molecule to molecule to atom, it moved on up. Okay, that's conduction. And so it works its way back up. Okay, and then the last but not least is radiation. And we've talked about radiation in here, electromagnetic radiation. Okay, so one form of electromagnetic radiation is infrared. So actually, this to me would be that thermal energy just traveling through space. Okay, at that point. It's funny, if you're like me, I'm like, wow, it takes like 100 million years to, or maybe it will go half of that, 50 million years to go up from the core to the top, and then maybe 50 million years to go back down. But 50 million years to go there, okay, and then a shorter time, I suspect, for the conduction, and the radiation is speed of light. So I just think that's so cool. So all of the planets, terrestrial planets, and the moon have cooled down like this, these three ways. Okay, so ooey gooey, right? So ooey gooey has consequences. The only two planets we've said were the terrestrial planets that have any liquid in them are the Earth and Venus, okay? Mars, open for debate. Mercury, cool down too much, and the moon, cool down too much. So if you have some liquid in your mantle, bless you. And actually the core, I haven't mentioned it, but the core has both a solid part and a liquid part. You know, I don't think this textbook differentiates, but when it says core, actually there's an inner solid and an outer liquid part to a core. But if you have that, you can actually have, and there are electrical charges within that ooey gooiness, you can actually create a magnetic field. So I brought in a picture of a magnet. This right here kind of reminds me of those little games where you used to kind of dress up the face with a mustache and eyebrows and hair or something, okay? So with the filings, the metal filings, and what did you use? You used a magnet, okay? So this is like a bar magnet. The pink lines are actually the invisible lines of the magnetic fields that are associated with all bar magnets. Okay, all bar magnets have a north pole and a south pole. The lines of magnetic flux go out the south and in the north, something like that. Okay, so these are just invisible lines. You can create a magnetic field if you have, this is my Duracell battery, okay, copper top Duracell battery. If you have a battery and then this thing wrapped around this, this is just a piece of metal just to kind of hold the wire steady, okay? But basically you take a piece of copper, you wrap it in a circular form, and then you put it in the other end of the battery, okay? So what you've done basically is taken electrical charges and it'll go like this and go back in, go like this and go back in. But it's this right here, electrical charges spinning like that creates a magnetic field. So you see the lines, flux lines there too. So what's this have to do with planets? Okay. Well, it looks like this. Okay. If your planet has some liquid in it, okay, if it's still geologically active, okay, that planet has a decent rotation rate, like the Earth. Okay, that jostling around, that rotation, and kind of think of your belly sometimes, it's like how there's fluid in there. Basically, those charges are just spinning around because of the Earth's got liquid inside of it, and that liquid has charged particles. So that's kind of like the battery creating these charges like this. So actually then at the Earth's poles, okay, we have rotational poles approximately. We have magnetic poles. Some of you guys may know that actually the magnetic pole is off by I think like 11 degrees or so. Maybe it's not that much, that seems like a lot. Maybe half a degree. It's not as much as 11. But the magnetic North Pole does not align with Earth's magnetic rotational pole exactly. Have you guys heard this idea of the poles flipping? Okay, yeah, this is exactly what we're talking about. We know that actually, okay, so I don't have my, if this is Earth's axis of rotation, okay, we've got north magnetic pole and south magnetic pole kind of going like that. Pink lines, whew, okay. We know that in the past, actually, Earth's north magnetic pole has been down here with our south rotational pole, okay. So it used to be, now it's here, and they flipped, okay, they flipped. Which is okay, but here in a minute I'm going to try to tell you that where the lines of flux come in to our, to our poles, okay, our magnetic poles. I get my poles mixed up. To our magnetic poles where the lines come in, actually we are vulnerable there. So during the flipping process, we basically have a hole that's the scary part. So anyway, there's the Earth. Now, I don't think I say it in my slides, but I said that like Venus is geologically active, but Venus doesn't really have a magnetic pole, a magnetic field around it, and it's due to its slow rotational rate. All right, so there we go, back to Earth. So here, this yellow here you see is actually energy coming from the sun. Now when we talk about the sun, we're going to see that the sun sends us light energy, the sun sends us X-rays, ultraviolet, our sun sends us infrared, all different types of radiation, electromagnetic radiation. The sun also sends us charged particles, okay, little charged particles that actually would sterilize our planet if those charged particles got to us. So thank goodness, and the reason we're showing you this slide is basically this kind of the blue ghosty thing right there, that is our magnetic field. That's the Earth's magnetic field. Sometimes the Earth's magnetic field is called the magnetosphere. It sounds like a comic strip thing, magnetosphere, okay? It's basically this protective layer that's created by spinning charged particles, okay? So there's the Earth's magnetosphere. Remember we talked about the solar wind, that basically when the sun turned on, it had solar wind. Think of those charged particles as being carried in the solar wind, and notice that they kind of create they elongate our magnetosphere on the other side. That's really the way it works. And within the last, I'll say, couple years, actually NASA has put a pair, I think, of satellite orbiting the Earth just to study the magnetosphere. I'm like, yay, NASA. Okay. The pink things there, where the pink things aren't the Earth. Actually, the pink things are outside the Earth. That's actually called the Van Allen radiation belts. You guys may have heard the name Dr. Van Allen. He's actually from Mount Pleasant. He's a local boy. Dr. Van Allen taught at the University of Iowa. I think he enjoyed teaching Intro to Astronomy. Okay, but just an astrophysicist. Just an astrophysicist. All right. So this actually is a photograph of something that's on my bucket list. Okay, this over here, these are the Northern Lights. Okay, and I haven't really ever seen them in fine form.
Don't they happen like around here every once in a while?
That you have to, the way the Northern Lights and the Southern Lights work is that you have to be kind of close to the poles. So sometimes actually the Northern Lights can kind of drip down to this far south. They have before.
Yeah, so like my uncle took a picture of it one time and I was like,
Yeah.
how did it even appear here?
Yeah. The other thing, the time that they would kind of drip down to as far south as us is if the sun is sending an extra dose of charged particles. Because the way this is all related is that if our magnetosphere gets overloaded with charged particles from the sun, basically it leaks. And where it leaks is in the poles. Okay? So then they kind of cascade down. So yeah. So, as far as the surface of the Earth, it hasn't always looked like it does now. It's kind of gone through changes over time. We talked about the period of heavy bombardment, okay? And I can't remember the date associated with that, but the Earth has definitely had its fair share of knocks. Remember, actually, those knocks brought us water from comets. Okay. Since we're still geologically active, we have both volcanism and plate tectonics, or tectonics that actually can resurface the Earth's surface. Erosion, that could be wind erosion or water erosion, that basically plays its part to make Earth's surface kind of ever-changing. Okay, so this is looking at impact craters. Okay, so there are just a few. There's one, I can't remember where it is in Iowa. There's actually, I'll say Wilson, Iowa, I'm not sure. But a lot of times if there is an impact crater, it's like got vegetation growing over it, that sort of thing. Okay, or it's been eroded by wind or water, glaciers, okay, or basically a volcano has dumped over it. Okay, so, but there are some remnants of craters. This is actually showing you a volcano erupting. Okay, actually two volcanoes erupting. This one down here is Mount St. Helens, which it didn't last very long, but in 1980, actually, it had a burp. I don't think it's a heavily populated region.
Call that a little more than a burp.
Yeah. Yeah, I think it reshaped its dome, yeah. But I would say it didn't go on and on and on like the volcanic activity in Hawaii, that sort
How
of
big
thing.
is that crater like in there?
I don't know. Which one?
Meteor
One
crater?
in Winslow, Arizona?
Yeah, the meteor crater one.
Big, real big.
Big.
Just
Yeah.
real big.
And the fact that it's still around means it's relatively fresh. So they're dating it at like about 50,000 years ago, which isn't very long. So, yeah, pretty fresh. One of the things that we're going to talk about is Earth's atmosphere. And do you see, like, especially in the Mount St. Helens eruption, you see all that, I'm sure there's particulates, that's what makes it kind of gray, but you can almost see the gases coming out of that volcano. Okay, so the burping, actually, it does release gases that then become gravitationally associated with our planet, and we call that our atmosphere. Okay, so changing Earth's surface. These are all different forms of erosion. There's the Colorado River with water erosion. The next one is glacier erosion. The next one is wind erosion. And the last one, something near and dear to our hearts, just simply water erosion from like something smaller than a Colorado, but just rivers. So actually, I'll mention it because we're going to get to that slide when we talk about Mars. Mars shows some of these same erosion features. Mars does. Okay, and actually some of them are very similar to water erosion on the Earth. So you're like, okay, then I guess Mars used to have liquid running water. You can kind of see these convection cells here in this middle one right here. Okay, tectonic forces at work. Actually, yet coming up, I'm going to show you how you can take the Earth's surface and kind of break it into major plates, and then where there's major tectonic plates, that's where you have your earthquakes and things like that. You have mountain buildings, and in the oceans you have your I can't remember what the hole is, but so the Earth's atmosphere is relatively thin and pretty darn precious. But one of the things, as we talk about the terrestrial planets, you know, we're going to see here in a slide in a minute that Mercury doesn't really have an atmosphere because it's so small and it really can't gravitationally hold on to one. It has a very thin one, Mercury does. The moon, nope, it has what we call an exosphere instead of an atmosphere. Then we go up to Mars. Mars has a thin atmosphere, and then Venus has a very thick atmosphere. Of course, Venus and the Earth are similar in size. But our current atmosphere isn't the composition of our current atmosphere isn't the way it's always been. The composition of the Earth's atmosphere has kind of morphed over time. Right now, we're about 77 or 80% nitrogen, 20% oxygen. Okay. So this actually kind of reminds me of a slide we looked at when we looked at different types of telescopes, or telescopes that you need to put in orbit about the Earth. Because again, you see those energies trying to go through the Earth's atmosphere, and notice that X-ray and ultraviolet don't make it down to the Earth's surface. Okay, but visible light does. And like the slide says, you've probably heard of the ozone layer. The ozone layer is associated with the stratosphere, right? Upper part of the stratosphere. And the ozone layer actually has 3 oxygen atoms, so they call it O3. And it's specific for blocking ultraviolet radiation. The ozone layer's been in the news because actually when we used to use CFCs as propellants and in our air conditioners and stuff, CFCs actually would attack ozone, and that's one chemical we don't want to be depleted. Let's see. So other worlds that don't have an atmosphere like this tend to not harbor life. In fact, as far as I know, Earth, this planet, is the only one that has life as we know it. I love that phrase, life as we know it. You know what I'm saying? But, yeah, biological life. And part of it is our atmosphere. So there's that lambda that you guys, we had for tonight's unit exam. And we talked about in Unit 2 that actually lambda means wavelength. And we talked about those different cousins of energy differ by their wavelength. And so the microwaves are the longest wavelength, of course, and gamma rays are the shortest wavelength. So we said actually the mnemonic device, Roy G. Biv, where red is the longest wavelength and violet is the shortest wavelength, actually all of that comes to and combines with the Earth's atmosphere to make our skies blue during the daytime. Okay. Specifically, what this is trying to show you okay, is, of course, you're looking down at the North Pole right there. And let's just go ahead and take it when the sun is high in the atmosphere, okay? When the sun is high in the sky at noon. Basically, the Earth's atmosphere is great for scattering blue light. So actually, you can kind of see these little ping-pongy things. Okay, blue light is being scattered. That makes our skies blue. If you're on the planet Mercury, let's take a planet that basically has no atmosphere. If you're in the daytime on the planet Mercury, the skies will be black. Okay, why? Because it doesn't have an atmosphere to scatter light like that. And so actually the scattering, when the sun is low on the horizon, this is showing you, looks like sunset, okay, in Florida. When the sun is low on the horizon, basically the scattering does such a great job that, I sound like Trump, such a great job, that actually the only thing that gets to the observer, the blue is entirely scattered out. So that's why our sunrises and sunsets have kind of that orangish reddish hue. One of my favorite things to do in the summertime is I like getting up early, but then you look at something like a stop sign when the sun is low on the horizon, and actually that stop sign is just glowing orange. And actually that's because all the blue is scattered out, because the sun is low on the horizon and it has to go through more of the Earth's atmosphere. I think that's cool. So in the last chapter in this unit, we're going to talk about planets around orbiting other stars. And we're going to see that most stars have planets, right? Most stars have a set of planets. Not as cool as our planets, but. And we're going to talk about something called the habitable zone. Okay? And this word just reminds me of habitable temperatures, for life as we know it to exist. Have you guys heard of these things called extremophiles, though? If you're into the Discovery Channel, you've seen that documentary. What an extremophile is, phile means love. They are little organisms that love like crazy cold or crazy hot temperatures, okay? So anyway. So the Earth's atmosphere has a great temperature for us, okay? And we do have just the right amount of what we call the greenhouse effect. Now, the other planet that has a significant atmosphere is Venus, and we're going to see Venus has too much of the greenhouse effect. Okay? So what the greenhouse effect is basically like a greenhouse does. Basically, you think of a lot of glass, and what glass does is it lets light through. Glass lets light through. And what it counts on is basically that light interacting with other things in the greenhouse to basically be converted into heat. Okay, it basically interacts, it gets them going faster and faster and faster. Okay, now, heat doesn't leave the greenhouse the same way that light comes in. So that layer of glass is pretty good thermal insulator. Okay, but it lets light in, it doesn't let heat out. Okay, so that's how carbon dioxide is in our atmosphere. Okay, basically what you're seeing is you can see the big thick yellow line on the left there. That's the incoming solar radiation from the sun. Okay, it strikes the Earth, and then you can see the little red squiggles coming up from the Earth. That actually is the infrared radiation. That's the heat energy. If you're going to sleep, dude, that's the heat energy coming up from the Earth. Yeah. So, and notice that heat energy doesn't leave like the solar, like the light came in. It's the greenhouse effect. So I like this figure from your textbook. It basically looks at, it doesn't include Mercury, but it looks at the Venus, the planet Venus, Earth, and Mars, and what would happen if it didn't have any greenhouse effect. So our average of temperatures would be negative 16 Celsius instead of 15 degrees Celsius. Okay? Venus would be negative 40. Venus, I told you, has a runaway greenhouse effect. There you go. Okay? How much does it add to the regular temperatures? 5, 10
So what would that
degrees
be in
Celsius.
Fahrenheit?
I don't know. I'd have to Google it. But I know water freezes at 0 Celsius, so that's definitely colder than freezing. Negative 16. It's not
Would
good.
Venus be colder than Earth?
Venus would be colder than Earth because Venus is farther from the sun. Yep. But check out how much hotter it really is.
Farther from the sun?
Oh, no, it's not farther from the sun. Check that out.
Why is that? That's weird. Is it because they're smaller?
Is it the rotation?
I think it's smaller. Must be smaller. That's a good catch. I know it's not farther from the Earth. Sorry. That's a good question. I bet it's the it's not that much smaller. I think it's like 5% smaller or something.
Maybe it is
So-
the rotation, like what he said then. Because it's super slow, right?
Yeah, but I don't think that would change because that's the yeah.
Other side.
Yeah. Good question, but I think it's its size. Very good. Okay, the little guys, Mercury and the Moon, both geologically dead, right? They're no longer geologically active. They look similar. I think when we kind of took a quick trip through our solar system, I showed you how the surface of Mercury looks very similar to the surface of the Moon, which hopefully we'll see tonight. Okay. So one of the things is that they aren't pocked a whole lot. I don't know if you remember though, but like our moon, we have the near side of the moon and the far side of the moon. Do you remember the far side of the moon is really ugly, really pocked? Okay, those dark areas are what we call mare. It doesn't have those mare on the far side. But yeah, the fact that they don't have a lot of pock marks means that actually they have resurfaced themselves some. So that does suggest that plate tectonics made that happen. Okay. With regard to an atmosphere, I already mentioned this, that actually Mercury, the planet Mercury has a thin atmosphere, and the moon actually has what's called an exosphere, which means it's just kind of oozing gas particles that actually don't stick around. I'm looking for a break here. Is this the next page? Is it the pages? Okay, let's go ahead and take a break, 10-minute break or so, and come back for more.